Let's get started. Today we'll be talking about hidden Markov models. This is probably the most involved topic that we'll be covering in class this term. And I say that because it relies on a combination of multiple ideas, from generative modeling to things like dynamic programming, which if you've taken, I believe the class is CS38, correct me if I'm wrong, then you've seen it before. But otherwise, we'll have to sort of go over the mechanics of concepts like dynamic programming in this class in the next week. So we'll start with a pretty straightforward task. It's one that we've seen remnants, a slice of in the previous lectures, but we'll talk about it a little bit more formally in a very specific way in this lecture. And that's sequence prediction. And to ground the idea of sequence prediction, we'll look at part of speech tagging. In part of speech tagging, the input is a sequence of words. Let's assume English words for now. And the output is a sequence of part of speech tags. And for simplicity, let's just think about the very simple kind, such as noun, verb, the determiner, pronoun, adjective, preposition, stuff like that. And so these are just three examples, right? So if the input sequence is fish, sleep, the target prediction is noun, verb, and so on and so forth. The dog ate my homework, noun, verb, determiner, noun, verb, determiner, noun. Then the fox jumped over the fence, determiner, noun, verb, preposition, determiner, noun. So that's the idea. So I think it should probably be obvious to many of you already, but just to sort of make it explicit, there are many challenges with this type of modeling. The multivariable, multi-length output is probably the most notable one, right? We need to make multiple predictions simultaneously, and the length of the sentences are not necessarily fixed. And so one idea is to say, okay, let's just treat this as multi-class prediction. So how many different classes are there? Well, sorry, excuse me. In multi-class prediction, we have a scoring function per class, and then we score each possible class, and then we predict the class with the highest score. So that's basically how it works. We have a weight per class, and then we score all the classes, and then we take the argmax over the scores. One of the challenges with this type of approach is that, well, okay, if there's only a few number of classes, this approach is quite sensible. And in fact, this style of approach is used, for example, in image classification, where given an image, we want to categorize what kind of object is in this image, one of k classes. But the problem with something like sequence prediction is that the number of categories is not fixed up front. In fact, it's variable length. But even if we consider all possible fixed length sequences with length m, then each individual class, at least in this very naive formulation, is one of all possible length m sequences of different part of speech labels. So just as an example, for length 2, these are some of the examples of different classes that we could be predicting. And of course, there are things we can do to prune this class. For example, we would probably never see determiner. It's probably not something that happens in English. But even ignoring those issues, naively, this is just a very big space of possible outputs. And in particular, there's an exponential number of possible classes in the length of the output sequence, where here I'm using capital L to denote the number of part of speech tags, or the vocabulary of the output space, if you will. And so that is 6 in this simple example. It could be much bigger. And the length is 2. So 2 to the, so 6 squared is 36. And as you can imagine, this number blows up very quickly. OK, so there's an exponential number of classes. This is not tractable in general. Okay, so just another illustration for length 3, is, it already looks quite hard to handle. And there's sort of two intertwined issues here. One is computational, one is statistical. And they're often interrelated to each other in machine learning. Computationally, we're treating, or as a modeling paradigm, in this very naive approach, we're treating every possible output sequence as a completely separate class. We're learning a completely separate scoring function, and then and because it's completely separate, we have to write this for loop that enumerates overall possible classes and then picks the class with the highest score. This is challenging for from both a statistical and a computational standpoint, because we have an exponentially large representation of the model representation of the phenomenon we're trying to capture, which means we need a lot of data to fit this model well, and we have a huge running time to actually make predictions in this model. And so it's bad in both ways. And indeed, there are many cases in machine learning where statistical efficiency and computational efficiency are very intricately tied together because they are related to the representational complexity of the model class. There are other cases where you actually have a trade-off between statistical efficiency and computational efficiency. There are certain phenomena that you try to model or learn where things that are statistically more efficient, so that require less data to fit the model reliably, are computationally harder. But here in this example, we see that statistical efficiency and computational efficiency are aligned, or at least their lack of efficiency in this particular case. Okay, so the other extreme, rather than treat every possible output sequence as its own class, is to say, okay, well, let's just ignore the sequence structure of the output and just treat every possible output token as an independent multi-class prediction per word. And so for the word I, we'll predict the part of speech tag for I independently. For the word fish, we'll predict the part of speech tag for fish independently, and so on and so forth. We could, of course, do something slightly more complicated, but for example, we could look at a window, but we're going to use this example, this simple example to illustrate this point. And then finally, after we made the predictions, we'll just concatenate them together. Okay, so the number of classes is equal to the vocabulary of the output space, or in this case, the number of part of speech tags, which is 6 in this example. And this we can solve using standard multi-class prediction. We'll learn a scoring function for each of the 6 classes depending on the input, which is a small slice of the input sentence, and then we concatenate the predictions together. We've completely destroyed the sequential structure, if you will. And so suppose we learn this model. So here it's a tabular model of probability of y given x, where if x is I, then we're modeling the probability of each of the part of speech tags. And let's say we fit this on the data, and these are the numbers we get. So for I, the probability of noun is 100% and 0 everywhere else. So this is a simple example for illustrative purposes. I am treating nouns and pronouns as the same thing for the purposes of illustration. So that's why I is a noun. X, if the input word is fish, then with probably 75% it's a noun, probably 25% it's a verb. Maybe that's the frequency in the training set, and so on and so forth. Okay, so then the prediction for I fish often is noun, noun, adverb. And the correct prediction is noun, verb, adverb. We've misclassified fish as a noun when it should have been a verb in this particular sentence. So the reason that we make this mistake is that we are ignoring sequential context. Right? So in isolation, fish is more likely to be a noun. That's what our model has learned. And that's actually probably true. I think that's typically true in any data set you collect of natural language. But conditioned on the previous word being a noun or a pronoun, I'm treating them equivalently in this particular example, then fish is more likely to be a verb. And that's something that is not captured in this very simple model. This is known as a first-order dependence. A first-order dependence says I want to model all interactions between adjacent pairs of words. In a zeroth-order model, which is what we saw in the previous example, we don't do. We could also model second-order dependencies, which consider all adjacent triplets of words. And arbitrary order basically gets us back to the exponential model that we saw in the very beginning. Any questions up until this point? I'm going to go into hidden Markov models next, but this is just to sort of set the stage for all the different desiderata and things that we should care about in making modeling assumptions. Okay, so a hidden Markov model is a generative model, and and I'm going to present a first-order hidden Markov model. You could generalize to higher orders without too much difficulty, although the math gets more complicated, or the notation at least gets more complicated. And so a hidden Markov model, a first-order hidden Markov model, is defined by the following 4 probability tables. We have the probability of generating yi given, of generating xi given yi. So if the current word is going to be a specific part of speech tag, what's the probability of that seeing that word? We have a transition probability from the previous part of speech tag to the next, or the current part of speech tag to the next part of speech tag, or equivalently from the previous part of speech tag to the current part of speech tag. I chose to do I plus 1 given I. Some people write this as probability yi given I minus 1. Doesn't really matter as long as your indexing is consistent. We have the start distribution and the probability that this part of speech tag leads to the end state, which is a special end state. The last one is sometimes not used. Sometimes it is. And I'm referring to y's generically as quote-unquote states, because that's the language that hidden Markov models are typically used to express hidden Markov models. In the example, a state is a part of speech tag. What is the state of the next word? What is the part of speech tag of the next word? That's the modeling assumption. So this is the graphical model representation. We have, and we saw this at the end of the previous lecture. We have a sequence of, we have a sequence of y's, and the y, condition on the y, we generate each individual x, and then the y depends on the previous y. So that specifies the entire probability distribution that looks like this. And again, the arrows specify the conditional independence assumption. So given yi minus 1, the probability of y only depends on yi minus 1, and so on and so forth. So what I just have up here is the joint distribution of an xy pair, where x and y's are sequences. And this joint probability distribution is factorized into these pairwise probability measures. So suppose we want to model P of x given y. Well, each individual x only depends on its corresponding y. So that's just so then condition on y, if we happen to observe y, under the hidden Markov model modeling assumption, then the probability of observing the sequence of x is completely conditionally independent of each other. So that's one property that we can deduce from just looking at the hidden Markov model. So okay, we model. Let's look at the number of parameters in these probability tables. P of y given yi given, or P of y plus 1 given yi. The number of parameters, if we take a tabular representation, is the size of the vocabulary squared of your output space. So in our example, that would be 6 times 6, which is 36. The number of parameters in P of xi given yi is the number of part of speech tags times the size of your input vocabulary. And then the bottom two probability tables are much smaller. They're linear vectors. They're not probability matrices, if you will. They're just probability vectors. So the complexity is really dominated. The representational complexity is really dominated by the number of parameters in the first two probability tables. So we saw naive Bayes in the previous lecture. And one might ask, what is the relationship between a hidden Markov model and a naive Bayes model? And there's a few different ways to express this relationship. And here's one way. In a naive Bayes model, if you just simply remove the dependencies between the neighboring y's, we get back a version of the naive Bayes. Of course, in naive Bayes, at least the way we wrote it in the previous lecture, each y generated multiple different x's. And here, each y only generates a single x. But otherwise, you get back just a sequence of naive Bayes models that are independent of each other once you chop off the dependencies, the sequential dependencies between the y's. So in some sense, a hidden Markov model is, in some sense, the simplest extension of naive Bayes that can incorporate sequential dependencies. Right. So, okay. So this is, just to be very explicit, we have this is p of x given y. So this is for a specific token in the sequence. If the current part of speech tag is noun, then the probability of x being fish is 80%. Probability of sleep is 20%. We assume that we have a 2-word input language and a 2-tag output language, output vocabulary. So noun and verb, fish and sleep. If the input is, the current part of speech tag is verb, then the probability of fish is 50%. The probability of sleep is 50%. And so the probability of observing fish sleep, given that y equals noun verb, is simply 0.8 times 0.5. And so this is just a grounded example rehashing what we saw in a couple slides ago. Yikes. Mic turned off. There'll be a little bit of silence in the video. Oh well. Okay. Sampling. So HMMs are generative models. Models the joint distribution between all of x comma y. And so as a generative model, we can generate samples from this distribution. And so first, let's consider a conditional distribution, p of x given y. So given it if we commit to a sequence y, which is a sequence of part of speech tags, what is the sequence of x? And because of the model structure of the hidden Markov model, we see that we can just generate the probability of each word completely independently of each other. So the probability of the word in the first spot only depends on the fact that the first part of speech tag is noun, and the probability of the second word only depends on the fact that the second part of speech tag is verb. This is a consequence of the hidden Markov model assumption. Okay, that's pretty simple. What about sampling over all of x and y without pre-committing to a y, without preconditioning on a y? And that's typically done via forward sampling. Sometimes people express this as a probabilistic finite state machine, which is basically equivalent to sampling from this model. And so you start with the start state, which is y0. And then you have the initial probability of having the first part of speech tag being either noun or verb. And then you sample y from P of yi given P of yi minus 1. If we end up at the end state, we quit. Otherwise, we sample xi from P of yi, and then we repeat this process until we, at some point, reach the end state. And that's how one would sample from this distribution in the full joint setting. Sometimes people don't use the last term, and because they fix a length. So if the length is 10, they just prefix it. Okay, so let's just take stock of where we are right now. What we've seen up to this point is the first order hidden Markov model. It is fully specified by these 4 probability tables, and they are multiplied together to model the joint probability between an xy pair where each of x and y are input and output sequences respectively. It is considered a memoryless model in the sense that you only need to know yk to model the rest of the sequence. So if I give you if I somehow observe x1 through k and y1 through k, and I want to model the distribution of the remaining x and y's, because of the hidden Markov model modeling assumptions, if we just look at these probability tables, once we condition on observing yk, it doesn't depend on anything else in our previous history. And this is what it means to be a memoryless model. As long as I observe the sufficient statistics of my current state, I have no dependence on the full history. Any questions? Okay. So next, I want to talk about the Viterbi algorithm, which is a dynamic programming algorithm for doing inference in hidden Markov models. How many of you have heard of dynamic programming or have seen it in class? Okay. And how many of you have not seen dynamic programming in class? Okay. Viterbi algorithm is an instance of dynamic programming. We have a recitation on dynamic programming this Thursday. So the most common prediction problem, which I haven't talked about yet because it requires the Viterbi algorithm, is predicting P of y given x. And in particular, not just predicting P of y given x, choosing the y that maximizes P of y given x. So we're given a sequence of words, and we want to compute the sequence of part-of-speech tags y that has maximal probability under the hidden Markov model condition on observing x. Now we can of course compute P of y for any specific y. We can compute P of y given x using Bayes' rule. I won't go through the exercise right now, but that's something that conceptually we can do. So then we can maybe write a for loop over all possible y's and then compute the P of y given x and then pick the y that has the highest P of y given x. That of course won't work as the length of y, as the length of the inputs and outputs increase. Because that takes exponential time. And so we need to do something smarter. And in fact, this is one of the reasons why people like the hidden Markov model so much, is because it has, because of the way it's represented in the specific modeling assumptions and conditional independence assumptions that it makes, it leads to very practical algorithms in terms of doing this kind of computation, which avoids an exponential blow-up. So this is Bayes' rule. P of y given x is argmax of P of y given x is equal to argmax over y, P of y comma x divided by P of x. And because x is fixed, because we're conditioning on x, and it doesn't depend on the free variable that we're optimizing y, we can ignore the denominator when we're solving the argmax. And then we can, of course, refactorize this as p of x given y times p of y. And these two terms are terms that we can just read off in our probability table. Right? So p of x given y completely factorizes into the individual probabilities xi given yi. And then p of y is just the sequence of probabilities from the transition probabilities from y minus 1 to yi. So now we've rewritten this problem in a form that can be explicitly computed by looking up values in a probability in the probability tables that we learn explicitly as part of the hidden Markov model. Okay. So I've just rewritten that derivation at the very top. So we want to solve argmax of py given x, and that is equivalent to argmax of because we're holding x fixed of this guy, which is equivalent to that guy. And so I'll just rewritten that up here. I should mention that I've gotten rid of this guy just for simplicity in this formulation, but nothing really changes conceptually. What I'm going to do right now is I'm going to break up this argmax into argmax of the very last output token and then the argmax of everything else. So the first 1 through n minus 1 outputs are in this argmax, and the last one's in this one. Nothing has changed in terms of the mathematical optimization problem. I've just simply did a rewriting of it. And I'm going to factor out the terms that depend on ym out, and then recombine everything else. So what does that mean? That means now we have a p of ym given ym minus 1 times p of xm given ym, and then everything else that doesn't depend on ym. And because this is a first order hidden Markov model, these are the only two terms that depend on ym. Again, I have not changed the optimization problem at all. I've simply just rewritten things in a way that's going to become very convenient to us computationally very soon. What we're basically doing is we're exploiting the memoryless property of hidden Markov models to arrive at a dynamic programming solution for solving this argmax problem. In other words, if we somehow have computed some of the a partial answer up to ym minus 1, then the only thing we need to do to figure out the answer for ym is through this probability table and through this observation xm. We don't need to, if we somehow figured out what we need to know for the first m minus 1 y's, we don't need to look at the previous x's. We only need to look at xm and p of ym given p of ym minus 1. Those are the only two things we need to look at to figure out the answer for ym. That's the memoryless property of hidden Markov models at work, and we're going to exploit that. So in general, the way dynamic programming works is it tries to maintain a set of sufficient. It tries to let's see, what's the right way to explain the intuition? It looks at the structure of the optimization problem, and it tries to find what is the minimal set of things I need to keep track of in order to compute the optimal solution for the remaining part of the problem. And if I could just pre-compute that, then that's the only thing I need to keep track of as I solve this problem. And then by the end, I can show that I've solved this whole problem without having to look over the whole exponential space of possibilities. And I'll walk us through this in very concrete form for hidden Markov models. So let us assume that the thing that we've computed is the best length k prefix ending in each tag. Okay? So what does that mean? That means at length k, so if we have a length m sequence, like a length 10 sentence, and k is 3, then we want to find the best length 3 prefix, so of possible y's, that end in verb, let's say. So this is equivalent to saying I want to find the best. This is equivalent to saying it's the best length k minus 1 set of y's, and then I force the last y to be verb, and it has to maximize this probability. Similarly, we can define it for noun, and we define this for every possible part of speech tag in our output vocabulary. We compute the best length k prefix that ends in each of the tags. So now we say, okay, what is the best? So now we know what is the best length k prefix that ends in verb. What is the best length k prefix that ends in noun? The claim is that if we want to compute the best length k plus 1 prefix that ends in, let's say, verb, we only need to look over the solutions we've computed for length k. So in this particular case, suppose there are only two part of speech tags, verb and noun, then we just need to take a look at this sequence. The sequence is this guy concatenated with verb, and this sequence is this guy concatenated with noun, and we concatenate verb to this guy, and we compute this probability. We concatenate verb to this guy, and we compute the probability, and we pick the one that's higher, and then we append verb to that sequence. Right, and of course, because we're going to do this process recursively, a lot of these the values in this argmax, like the probabilities, are pre-computed because of the hidden Markov model structure. We've already pre-computed part of these probabilities of the partial sequences. So I'm going to go through another example of this. But this is sort of the high-level idea. And this is a recursive definition. And once we've started this recursive definition, we just recurse from k equals 1 to k equals the full length, and then after that we can just read off the solution for k equals m. I'm going to go over another version of this example in a different form, just because I feel like different people learn in different ways. But before I do that, were there any conceptual questions at a high level? Yes?
So to me, this kind of looks like a greedy algorithm. I'm not sure if that's accurate, but is there a possibility, like, let's say your second POS, most likely one is like X, and then but that actually makes all the probabilities for the third POS like very small.
Yes, that's entirely possible. That's why we have to keep track of. That's why we have to keep track of the possible endings of all possible part of speech tags. Oh, okay. Right. So the question is, okay, if we think the best part is, so there's one of these two. So ending in verb or ending in noun is going to be it's going to have a higher probability than the other one. Right. But we're going to keep track of both of them, because both of them could transition to the next token. And of course, one of those transition probabilities could be very low, one of them could be very high, and that's fine. And we're going to prove that it's sufficient to just keep track of all the possible endings at each fixed length prefix solution. And I will go over another version of this example in a more kind of dynamic version of this example. So here we're going to have three part of speech tags. So noun, verb, and determiner. And we're going to start with y equals 1. We're going to start with the base case. In the base case, it's trivial. The best length 1 sequence that ends in verb is verb. Nothing to compute. Of course, we're going to store. We're going to store at every k. We're going to store the solution, and then we're going to store the probability of the subsequence, of the length k subsequence. So we're going to store the probability of the first word being verb, determiner, or noun. And then for k equals 2, we're going to solve for the best length 2 sequence that ends in verb, that ends in noun, and ends in determiner. So let's start with verb. So what the algorithm does is it only looks over the best length 1 subsequence that ends in verb, determiner, or noun. So it considers what is the solution from here, what is the solution from here, what is the solution from here, what is the probability that I've accumulated so far for each of these 3 as well. I'm going to try to transition from verb to not verb. I'm going to try to transition from determiner to verb. I'm going to try to transition from noun to verb. I'm going to multiply those transition probabilities. And I'm going to also multiply by the observation probability that this guy is verb. And then I'm going to choose the one that has the maximum probability, and I'm going to commit to it. And now I'm going to do this again for the other one, so the best length 2 sequence prefix that ends in determiner, the best length 2 prefix sequence that ends in noun. I'm going to do that exact exercise and do a for loop over these 3 solutions. Try transitioning from verb to determiner, determiner to determiner, noun to determiner, and look at the new updated probabilities of the length k prefix, and then choose the one that has the highest probability. And same with noun. So now I've computed the solution for the best length 2 prefix solutions that ends in verb, determiner, or noun. And you can even just, if in this pictorial view, you can even read off the solution. The solution here is noun, verb, verb, determiner, determiner, noun. And again, I'm going to store the partial probabilities. Just for convenience, because I'm going to use it in the next iteration of this recursive definition. And I'm going to do this again. I'm going to do k equals 3. Try transitioning from this prefix from verb to verb, transitioning from this prefix solution from determiner to verb, from noun to verb, multiply by the probabilities of the transition and the observation probabilities of the x. And we just keep doing this until we reach the end of the sequence. And the claim is that, again, the claim is that we only, in order to find the optimal solution, the optimal length 3 prefix solution that ends in verb, we only need to check a pending verb to one of these 3 solutions. We don't need to check all the other solutions. That's the claim. If we can prove that claim, then we can prove this algorithm is correct. So, right, so verb is not, so in particular, we have excluded verb as a possible, we've excluded verb as a possible solution. The only solutions that we're going to consider are noun, verb, determiner, verb, and determiner, noun, verb. Those are the only 3 solutions we're going to consider. We've excluded everything else. In particular, suppose that verb was the optimal solution. Suppose, and somehow this algorithm was wrong. So this is a proof by contradiction. Well, suppose that this had higher probability. Then, by the hidden Markov model assumption, the probability of verb, and noun, verb differ in exactly 3 terms. They differ in this guy, and this guy. None of these 3 terms depend on Y3. And so if the probability of verb was higher than the probability of noun, verb, it would have been the solution for the length 2 prefix. And one can, of course, make this statement more mathematically rigorous and do an actual proof. I'm just showing you sort of a sketch of a proof for a concrete k equals 3. But you could take this and make it more rigorous for general k. But that's the idea. It's a proof by contradiction. Yeah. And so we store this part prefix solution, and then we keep going. Any questions? Yes?
Why are there two arrows going from Y to verb?
Going to where?
So,
Yes. So the best length 3 prefix solution ends at determiner could come from verb. The best length 3 prefix solution from noun could also come from verb.
okay.
Nothing in this algorithm says that these. The algorithm only says that there can be only. The algorithm only says that there is only one incoming arrow.
Okay. Intuitively, if we're only looking at pairs at a time, I don't understand why if the best sequence that ended in noun for Y2 was the determinant. So the second column, the first one. So no, noun. So ended in noun, started in determinant. Determinant, noun.
Sorry, hold on. I have like near whiteboard blindness. Oh, okay. Yeah, okay.
But it's not the same in the next iteration. Does that make sense? Y3n doesn't come from Y2d, but Y2n goes to Y1. Why is it not symmetric if each time it's just pairs?
Okay. I'm trying to parse your question.
Sorry, I can rephrase it again.
Yeah. Do you want to come up here?
I think the probability of a determinant going to a noun
Yes.
tends to be the same every time.
Yes.
So why isn't it?
Because there's a word here. There's a word like fish, or there's a word like.
Oh, because it's a specific word.
Yeah. There's a word. Sorry, I didn't. There's an x. There's an x associated with each. Yeah. There's an x there. That.
Okay.
Yeah. But that the x again. The x is conditionally independent given the y for each frame in the sequence. So I didn't show it because it didn't add to the arrows.
Right.
Because the arrows is only the probability of yi given yi minus 1. Like, for example, if it's like I fish often, those are the x's, then we also that's part of the probability that we compute. Any other questions? Okay, so that's basically a summary of the Viterbi algorithm. For every k from 1 to the end, we iteratively solve for each for the best length k prefix solution that ends in every possible output tag. And the claim is that solving this, we only need to look over the prefix solutions that we computed in the previous time step. And then at the end, we just we loop over all possible z for length k equals m, the last one, and then we simply pick the one that has the highest probability, and we're done. Yeah. So we went through all this work to make this claim. We only need to look at the sort of the solutions that we've memorized, the prefix solutions that we've memorized for the previous iteration of this algorithm. There must be some benefit. Can anyone tell me what the benefit of this algorithm is? Primarily from the running time. Recall that the naive algorithm that would have to write a for loop over all possible sequences of y, it runs in exponential time. This algorithm does not run in exponential time, yes. It is quadratic, yes. It is linear the length of the sequence. Yes, so it's linear the length of the sequence and quadratic in the number of part of speech tags. So it is L squared times m rather than L to the m. And for long sequences, even for sequences of length 10, this is a huge difference. And the intuition, again, has come from exactly the fact that when we want to compute the best length, when we compute the best, so one of these will be the best answer. And those answers, don't require computing all possible paths. It excludes all except for the paths that we computed previously. And again, this is an instance of dynamic programming. And dynamic programming, typically, the way dynamic programming works is that there's some partial solution that if you solve for the partial solution, it's sufficient to use that to solve for the rest of the solution, and you just recursively call the subroutine that solves for this partial solution as it grows, and then at the end we only look at the partial solution or for the full answer. I should just mention, dynamic programming, of course, appears in places far beyond machine learning. And in fact, I would say that dynamic programming is one of the most central computer science concepts in period. And is used all over the place to achieve efficient algorithms at scale that would otherwise be very expensive computationally. Okay, so I'm just going to walk through a numerical example very quickly. This is an even simpler example: fish sleep. So 2 words and 2 part of speech tags. So everything is a little bit smaller now. And so we start with the initial start state. We observe that the first x is fish. So we observe that x1 equals fish. We compute the probability of transitioning to the from start to verb and start to noun. These are the two probabilities. This is the probability that let's see. This is the probability that verb generates. Sorry, did I mix dice? Probability that noun generates. Sorry. That noun generates fish, and verb generates fish. Excuse me, sorry. The first number is the probability of transitioning from start to verb and start to noun. And the second number is the probability of generating fish given that we're at verb and generating fish given that we're at noun. Okay, so this is the length 1 prefix solution and the corresponding partial probabilities of that length prefix subsequence. And then we look at the length 2 and we compute that solution for coming from either one. So either coming from verb to verb, a verb to noun, or noun to verb, noun to noun. That's the top and bottom of these 2 rows respectively. We pick the one that's argmax, and so on and so forth. And then at the end, we look at these 2 solutions. We pick the one that's higher. Okay. So this is just another example of the same process. I just made it smaller. I used a smaller example so I can go through some numerics. But that's the basic idea. Okay, so one issue is what will go wrong if you have long sequences. These numbers start getting kind of small, and you can underflow because you're multiplying many numbers together. If this was length 10, length 20, length 30, these small numbers, which are all less than 1, by the way, will get multiplied together and decay exponentially quickly towards 0. And so in practice, what people often do is they run the Viterbi algorithm using log probabilities rather than the actual probabilities. All that basically means is that instead of multiplying things together, we're adding the logs of these things rather than multiplying them by the original probabilities. Just the log, sum over the log of the probabilities. But in terms of the structure of the dynamic programming, nothing changes. Instead of multiplying these probabilities together, we sum over the log of their probabilities. Okay, so just to recap, the reason why we don't use independent classification for this problem is that we want to model sequential dependencies between the words. Of course, we want this modeling of the sequential dependency to be compact enough that we can actually learn and do computations over our model efficiently, rather than having it blow up exponentially, either in terms of sample complexity or in terms of computational complexity. And so that is what leads us to the hidden Markov model. And in hidden Markov models, we have a first-order dependence. This is also known as a memoryless dependence. And there are many algorithms that do computations for this over the hidden Markov model that exploit the fact that there's this first-order dependency in order to arrive at efficient algorithms using dynamic programming to do computations over the hidden Markov model. And yet, the hidden Markov model also captures some notions of sequential dependence. So for a certain class of applications, and certainly historically, the hidden Markov model occupies a quote-unquote sweet spot in terms of expressiveness. We can capture aspects of sequential dependencies and efficiency. It is not overwhelmingly expensive to train and to do computation over these models. Any questions before I move on to the training algorithms? Okay, so let's start with supervised training. So we're given a set of XY pairs. And the goal is to estimate P of X comma Y given these XY pairs. We're going to do this using maximum likelihood. Just an aside, just like in as before in the previous lecture, we often write these things using matrix form just to make the pseudocode more compact and in some cases vectorizable. So typically we think of there being a transition matrix and an observation matrix. Transition matrix is just P of the yi given yi minus 1, and the observation matrix is just P of X given y. So just rewriting things in matrix form. Nothing has changed. Okay, maximum likelihood. So given a training set of XY pairs, we want to and assuming that these XY pairs are sampled independently from the true test distribution, we want to maximize the product of the probabilities of observing these XY pairs given our model, which is basically just this term over the parameters of our model. And that gets factorized because of our hidden Markov model assumption into these probability tables. And you can derive in a fairly straightforward way that this maximum likelihood solution is just counting, just like a naive Bayes. So the transition probability of going from B to A, so if A and B are part of speech tags, is just the frequency with which that happens. The probability of observing a given X, given a Y, is just, again, the frequency of observing that happens. And again, if you want to go through that exercise, like in a previous lecture, where we derive it for naive Bayes using by minimizing negative law likelihood, you can sort of get the same answer here. It's a pretty straightforward exercise. So, like in naive Bayes, in the fully supervised setting, it's just counting statistics, super easy. Why is that? It's because of the conditional dependence assumptions. Everything decomposes. So, just like in naive Bayes, with the conditional dependence assumptions we impose here, everything decomposes into these little products, and just like in naive Bayes, if you have multiple different x's, but they're conditionally independent, again, everything decomposes into just frequency counting. You can show just from the same derivations that these independent assumptions allow us to just do frequency counts. Number of parameters, number of A matrix is number of tags squared, part of speech tags squared. Observation matrix is the number of words times number of tags. Those are the two big parameters of this model. And this also allows us to avoid modeling word-word pairings. So, for example, if the number of tags you have is around the order of 10 to 20, and the words are in the 10,000, sometimes much more, this is much more efficient than directly modeling word-word transitions. This is we saw a similar argument in the embeddings lecture for word2vec. Okay, so the last part of the lecture is going to be on unsupervised training. What if we just observed a bunch of X and we don't observe the Y? So we just see a bunch of sequences of words and we don't observe their part of speech tags. This is actually quite common because annotating for part of speech tags can be expensive. We would have to hire someone to do the annotations. But suppose we still want to model P of X comma Y, even though we don't have labels for Y. So how do we do that? Why do we want to do that? And perhaps let's answer the why first. And this is sort of a rehash of some of the same points that we touched on in previous lectures on unsupervised learning. But let's just go over it again in the context of sequence modeling. Supervised data is sometimes hard to acquire. It would require annotating the part of speech tags. Unsupervised data is much more plentiful than supervised data. Just download some text from, let's say, Wikipedia. And there might be other tasks that we want to use this model for. For example, we can sample new sentences. We saw at the end of the previous lecture, and we'll see more in next week in the deep generative models lecture, that these generative models can actually sample things that are quite interesting. Of course, the modern approaches blend these classical approaches with deep learning to get maximum effectiveness. But nonetheless, these methods are rooted in probabilistic modeling. And so if we can build a good generative model of the training distribution, we could, in theory, generate data that looks like the training distribution. And this is, in fact, the topic of mini project 3, where you have to generate your own content. So now let's go over the how. So the most common algorithm for solving these unsupervised learning generative models, for fitting generative models in an unsupervised way where some of the variables are not observed, is through an algorithm called the EM algorithm. So if we had the Ys, so if we observed everything that was latent or not observed in the training set, then everything reduces to maximum likelihood, like in the supervised learning case. The problem is we don't have the Ys. If we had the model parameters, we could predict the Ys. We could actually compute the probabilities of observing these Ys. So we have this chicken and egg problem. And so the EM algorithm basically says, let's initialize the models of the parameter arbitrarily, randomly even. And then we predict the probability of observing the Ys, the variables that we don't observe in our training set, for each training example. That's called the E step, or the expectation step. And then given this prediction of the y's, let's use those y's to estimate a new set of parameters for our model. That's the M step, also known as the maximization step. And we repeat until we converge. This is not unlike the structure of k-means clustering, where you assign cluster memberships, then you estimate new cluster centers, then assign cluster memberships and estimate new cluster centers. That is actually, the k-means algorithm is actually also an EM algorithm. But here we're going to predict the probabilities of the variables we don't observe, use all the variables, then use those probabilities to treat it as a supervised learning problem to estimate model parameters, then repeat. So the maximization step is pretty trivial, because it just reduces the standard supervised learning. The expectation step is the one that is a bit tricky. So what we do in the expectation step is we want to predict P of yi for every given input sequence x. And P of yi is essentially the marginal distribution of each y. And it encodes the model's current beliefs about what y should be given the model parameters. This is just a reminder of the definitions of the parameters we want to estimate. Suppose we already did the expectation step, then this is what the maximization step looks like. So this is supervised learning, where we're just doing hard counting. In unsupervised learning, we do soft counting. So our model, our current parameterization of the model, we used it to compute these probabilities for this input sequence, and we used to compute these for the input sequence, and we just simply do a frequency count, just as in the supervised learning case, but instead of hard counting, we do soft counting. And you could derive that this is the correct thing to do, given our current beliefs about what the y's are. So the trick is to basically compute these two numbers. We have to compute this probability and this probability. And if we can compute that for all the training data, then that's the E step and this is the M step. Okay, so the algorithm for computing those probabilities is called the forward-backwards algorithm. And the forward-backward algorithm is another instance of dynamic programming. So a little bit of notation. And again, I think it's going to be hard to digest this all in this one lecture. So it's important for you to just get a feel for the structure of the algorithm and to allow you to dive deeper into it later. But the basic idea is that we have this prefix solution and a suffix solution. And the prefix solution is basically modeling the probability of observing the first, let's see, I'm going to use I to index the first I words, given that the ith part of speech tag is whatever free variable z. The suffix solution is modeling the probability of observing words I plus 1 to m, given that yi, conditioned on yi being part of speech tag variable z. If we can compute these prefix and suffix solutions using dynamic programming, then we can compute these marginal probabilities by simply combining the two. We can likewise compute these pairwise marginal solutions for pairs of adjacent y's by likewise combining, by doing combinations over these alpha and beta prefix-suffix solutions. So computing the prefix solutions is called the forward algorithm. Computing the suffix solutions is called the backwards algorithm. And the full algorithm is called the forward backwards algorithm. So why is this potentially hard? Why even do dynamic programming? Well, if you think about this solution, right? This solution requires, this prefix solution requires enumerating over all possible y. At least if you think about the laws of probability and how we want to use the probability tables that are explicitly part of the model, this actually requires summing over all the y1 to yi minus 1, which can take exponential time. But we can instead compute these solutions recursively using the previous solution. So the base case is, again, straightforward to compute for the first solution. Then for all subsequent solutions, it's just a combination of the previously computed prefix solutions. And I won't go into over the details, but that's the high-level idea. It's not that hard to prove, given the same proof structure. One thing to note is that the Viterbi algorithm is very similar. The main difference is that the Viterbi algorithm replaces this sum with a max, with an argmax. So, whereas the forward algorithm just does the sum. So it's computing the full marginal solution. The backwards algorithm looks very similar, but it's run backwards. So the base case is the last token in the sequence, and then it works backwards. So this algorithm is actually the hardest part about this algorithm is actually making sure your indexing is consistent. As long as you make sure your indexing is consistent, this algorithm is actually very simple to implement. Yes?
Do you have any thoughts, I guess, on where expectation maximization has, I guess, different use cases or different applicability than something like Gibbs sampling, where you're you're kind of recursively sampling conditionals?
Right. So okay. So EM and Gibbs sampling have a complicated relationship. So there are algorithms where, so it depends on what you're Gibbs sampling on. Let me just say this up front. It depends on what you are Gibbs sampling on. For example, for some models, I don't have a polynomial time algorithm to actually compute these numbers. For hidden Markov models, I do. I just presented it to you. For those algorithms, since I don't have a polynomial time algorithm, I can use sampling to compute these numbers. And for instance, we can use Gibbs sampling. So there's a complicated relationship between Gibbs sampling and EM algorithms. One way that they intersect is that for complicated models where it's still intractable to compute these marginals in polynomial time, you use Gibbs sampling and just do an approximate solution. So that's the full algorithm. We run forward, compute these alpha prefix solutions. We run backwards to compute the beta prefix suffix solutions. And then for every training example, we run forward and backwards. And then for every token in the part of speech tag sequence that we don't observe, we compute these marginal probabilities using the alpha and beta vectors. And that's the forward backwards algorithm to solving the E step of the EM algorithm. Any questions so far? Okay, so just to recap, our training data is only the input sequence is X, and then there are some variables in our generative model that we don't observe. We call them Y. More generally, if we were to work on generative models beyond what people care about in supervised learning. So in supervised learning, there's a special variable Y that we care about predicting. And the way I framed unsupervised learning is that we don't observe this Y explicitly. More generally, generative models, you could have a data set where you don't actually care. There is no Y. There is no special variable. It's just a bunch of data X, and I want to build a generative model over this data X. Like I want to do deep fake or whatever, right? And so if for these types of models, there are variables that we observe, and there are variables that we don't observe. And in cases where there are variables that we don't observe, we need to build it, and we still want to build a full generative model, then we need to do something like the EM algorithm to actually fit the parameters of the, for the variables that we don't observe. The Ys are also known as hidden states. That's why this is called a hidden Markov model, in fact. I should also mention that the EM algorithm is not guaranteed to converge to the global optimal solution. It is only guaranteed to converge to a local optimum, just like in k-means. So I think the last thing we'll talk about, yeah, this is the last thing we'll basically talk about, is initialization. How do you, for example, how do we choose a number of hidden states? How do we initialize the probability matrices? Choosing a number of hidden states is, of course, I think as a running theme in this class, it's an art form. There's no science, there's no real hard science in how do you do it reliably in practice. The theory is a bit lagging in this respect. You do validation. If you know for a fact that it should be this number of hidden states based off some other data, then you can just set it as that number of hidden states, or you can just do validation. Okay, so just to recap, today we saw sequence prediction and hidden Markov models. It is a generative model that models pairwise dependencies in sequences. You could think of it as the simplest extension of naive Bayes to be able to model sequential dependencies between the Ys. It's compact in that it only models the pairwise dependencies between Ys, and therefore we can exploit a lot of that structure to design efficient algorithms for learning and for prediction. Of course, this algorithm this approach has many limitations. The main one, of course, is that it makes so many independence assumptions that it may lead to poor predictive accuracy. So if your goal is to predict the sequence of Ys as accurately as possible, given a sequence of X, you may not want to use a hidden Markov model. And there are links on the course website to other to models that perform better in a purely focused supervised learning setting. Any questions? Okay, so I know that was a lot, and so the next lecture on Thursday, we're going to talk about hidden Markov models again. But the lecture will be sort of unstructured, so you could think of it as a glorified office hours. I find that once people have a chance to digest the material a bit, questions will start coming up. So we're going to go over the material again. If no one has any questions, I'll just go over the same lecture over again. But usually people have questions. And next Thursday, no, I'm sorry, that's wrong. Next Tuesday, we'll be looking at deep generative models, so how to combine some of these concepts that we saw this week with deep learning, and of course recitation on Thursday in recap of